Hello, and welcome to my video. My name is Norman LeMay, and I am your statistical instructor. And today, this video is on hypothesis testing when we have two independent populations. So in this video, at first, I'm going to lay the foundation for this type of hypothesis testing. And as always, we're going to use technology, and I do have separate technology videos available. But we will, in this one, I'm going to make a little bit of a change, and that is our change is going to be, I'm actually going to work the example out, or somewhat. Okay, again, I don't believe in all the calculator computations and so forth. So without further ado, let's get started. Cue the music. All right, so let's talk about two independent populations. So for example, suppose a researcher is interested in whether or not doing diet and exercising helps to lose weight more so than just doing diet only. So the question is, does the diet and the exercise help a person lose more weight over just, let's see, what is that, dieting? That's what we're taking a look at. Another thing is bargain valued shoppers. So what about the prices? On average, we go to Walmart, we go to King Soopers. Some people say, I go to Walmart because it's cheaper. So the question is, are the prices of groceries at Walmart cheaper than the prices, say, at King Soopers or Safeway? Or how about FaceTime on cell phones? The FaceTime on cell phones between men and women. Okay, so do one or the other, is there a difference? Is there a difference between how men and women, how much time on average that they spend on their cell phone? So all three examples do have something in common, and that is the two populations are considered to be independent, meaning that no subject could be contained in either population. We've seen matched pairs where the subjects is within both populations, but in this case, the subjects are not. So let's take a look at our working example and get an idea about what's going on. Okay, so our first example, let's take a look. Choco Cookies claims that they have the most chocolate chip in their cookies. They randomly sampled 11 of their chocolate chip cookies and found that the average number of chocolate chips per cookie is 7.2 with a standard deviation of 1.1. Choco Cookies randomly selected 12 chocolate chip cookies from their competitors and found that on average there was 6.1 chocolate chips per cookie with a standard deviation of 1.8. Is Choco's Cookies claim valid with a significance level of 0.5? All right, so that is going to be our working example. All right, so now what we would like to do is based off of this, is to define our population. So let's let mu1 be the average number of chocolate chips in each cookie for Choco Cookies, and let's let mu2 be the average number of cookies for the other brands, their competitions. All right, so now that we have this, notice that based on the question, does Choco have more chocolate chips in their cookies, we can now state our null and our alternative hypothesis. So let's just note that the null is going to be mu1 equals mu2, and the alternative is that mu1 is greater than mu2. So let's just observe that we do like we always do, and that is bring mu2 over to the other side and write this as a difference between the two population means. So with this information and what we have here is notice that since the population is defined using mu1 minus mu2, when we go out and collect our data, all right, from population 1 and from population 2, then notice we're going to have to compute an x bar 1 and we're going to have to compute an x bar 2. All right, so that means that when we form the differences, we get x bar 1 minus x bar 2. And that means we get a new random variable. Yet again, ta-da, cue the music. All right, so now what I'd like to do is to investigate and discuss the distribution properties for x bar 1 minus x bar 2. Under the normality assumption, we have the fact that Choco brand is going to be distributed normal with a mean mu1 and a standard deviation sigma 1, and the other brands are going to be distributed normal mu2 with a standard deviation of sigma 2. Now, we can have slight departures of normality. The t-test is what we call robust against slight departures, so we probably should investigate the normality assumptions of our data set when we collect the data set, because normally what happens is that our data is usually less than 30. So greater than 30, we got the central limit theorem that kicks in as always, and that could be a really nice friend of ours. All right, so the fact now is that if, and under the assumption that X bar, or that the first population, Choco brand, is normally distributed, then that gives us the fact that X bar 1 is going to be also normally distributed, and its mean will be mu1, and its standard deviation is going to be sigma 1 over the square root of n1. And with the other brand being also normally distributed, we know that X bar 2 is also going to be mu2, comma sigma 2 over the square root of n2. Okay, so now when we formulate that difference of x bar 1 minus x bar 2, then what is its distribution? So again, we have the differences of two normal random variables. So the nice thing is when you take the difference of two normal random variables, then that distribution is also normally distributed. So now that we have normality with the difference of x bar 1 minus x bar 2, then the question is what is the mean and what is the standard deviation for those differences? So the mean is going to be denoted as mu sub x bar 1 minus x bar 2, and probably using common sense again, we would think that maybe it's just a difference in their population means. And lo and behold, this is true. So the mean of the differences is mu1 minus mu2. The standard deviation is denoted as sigma sub x bar 1 minus x bar 2. And let's just note that it's going to be a little bit different. It doesn't follow the flow of our intuitiveness, but it's going to be sigma 1 squared over n1 plus sigma 2 squared over n2. So at the end of the day, it's really kind of nice that when we have our new statistic from the data of x bar 1 minus x bar 2, that also falls out to a normal distribution with those just mentioned parameters. So now that we have the distribution of the difference of x bar 1 and x bar 2, now we can go into our inferential component. just recall that a test statistic is something that is in the form involving something involving the data and something involving a statement or the current status of a situation involving a null hypothesis. So we've seen this over and over before. So our test statistic is going to be something involving the data minus something that we have hypothesized, usually under the null hypothesis. Well, not usually, it actually is. Divided by the standard deviation from that thing that comes to us from the data. Now, we just talked about the distribution properties of x bar 1 minus x bar 2. So let's just notice that these are normal. So it wouldn't be a huge surprise, I don't think, that the test statistic is going to be a z-test statistic, and it's going to be in this form of x bar 1 minus x bar 2. There's something from the data minus something that we've hypothesized under the null hypothesis divided by the standard deviation. And recall that the standard deviation of that random variable x bar 1 minus x bar 2 is that thing that's down there in the denominator. But wait a minute, we don't know sigma 1, nor do we know sigma 2. So again, we run to our good old friend, the t-test statistic. So we substitute S1 and S2 for sigma 1 and sigma 2, just like we've been doing, okay? And this now changes to a t-test statistic, where the degrees of freedom, using a conservative route, if you will, is going to be the smaller of n1 minus 1 or n2 minus 2. But we do have another form for the degrees of freedom, and it is this really, really ooky-looking formula that is based on a guy who did some work, and his name is Satterth? I don't know. Well, let's just put his name up there, and you tell me how to say it. Satterthwaite. Okay, this is what technology uses for us, and this is the formula right here that is used to compute the degrees of freedom, which notice that this is basically just some averaging and pooling of the standard deviations and their sample sizes. And, can you imagine having to type that into your calculator? Yeah, been there, done that. It is not nice. So we use our t-test statistic. Using technology, we'll use that Satterth formula to compute. It's more accurate. It's better to use a conservative route, meaning that you would probably commit a type 2 error. So this formula here for the t-test statistic, using this degrees of freedom, n1 minus 1 or n2 minus 2, you would, if you use this, you could be committing a type 2 error. And recall that if an error is committed, the preferred error is the type 2 error that's going to be committed. So that pretty much discusses that. And so now we have all the information that we need, that we can now move on to finishing up our opening example this time. All right, I'd like to go ahead and complete our opening example. So let's just recall that the null hypothesis was given, and we already discussed the null hypothesis. So now, based off of our prior discussion, we can go ahead now and compute the test statistic. So using the formula for our t-test statistic and the fact that the variances are not the same, we have our test statistic at 1.784. So the question is the distance between the difference of these two means, that is the 7.2 minus the 6.1, is those differences far enough away from 0, that is mu1 minus mu2, under the null hypothesis? Is that 1.784 far enough away to say, yeah, there is a statistical significant difference? Or if not, then the 7.2 and the 6.1, the difference, although practically different, is nothing more than innate random variability within our data set. So the way that we can determine that is to compute the p-value. So I computed the p-value using technology. So either StatCrunch or some other technology, probably your TI-84 calculator. I come up with 0.0454, taking this out to 4 decimal places. So let's just recall earlier we stated that the degrees of freedom is the sample size minus 1, the smaller of those two. So if we were to go that route, then we could compute the p-value based on 10 degrees of freedom, because 11 minus 1 is 10, and compute the p-value. So I went ahead and I did that. So notice that the technology came back and spewed out that this p-value is based on 18 degrees of freedom. But notice that using 10 degrees of freedom, which was recommended or is a way of computing the p-value, using the smaller of the two sample sizes minus 1, is 0.040524. And notice that we get two different results based on our significant level of 0.05. So I'm going to go ahead and use the output from the technology, because that one is more accurate, what is used, what should be used, rather than the sample size minus 1. So based off of this, we can come back and say, technically speaking, the p-value is smaller than the alpha level, so we will reject the null hypothesis. But notice, this isn't anything staggering. This isn't really anything that they can go out and grandiose gloat about, although their marketing department will probably come back and say, hey, we had this done, and we are showing that we have more chocolate chips per cookie on average, than our competitors. So this is one of those cases where we are just on the other side of the fence line of rejecting the null, and really we should technically be careful. But to move forward, let's take a look at our interpretation. So at an alpha level of 0.05, the data shows that Choco chocolate chip cookies average more chocolate chips than their competition. All right, so now I'd like to present some little tongue twister there. Now I would like to discuss some conclusions from our video. I feel like I should have a pipe. Where's my glass of scotch? Let's talk. We talked about formulating the null and the alternative in two different ways, usually involving the inequality population parameter on either side. But the popular method is to bring the mu2 over and talk about the differences. That way, when we have the differences, that gives us something involving the data that we can work with. Notice if, you can't compare x bar 1 and x bar 2. So it gives us a way of talking about the distribution forms that new random variable. And we found out that we use a t-test statistic as the two sigmas are unknown. And, push comes to shove, you just use the smaller of n1 or n2 and subtract 1 from each of those. Use the smaller of those two for your degrees of freedom to construct your p-value. And as a note, usually there is two forms when it comes to t-testing with two population parameters. When you get to three or more, the whole ball game changes and it goes into what we call an ANOVA. But for 2, it's either the populations are going to be dependent or the populations are going to be independent. And it is up to you to identify which paradigm you're in, because performing the wrong t-test could be disastrous. So we don't want that. So that wraps up our video, and as always, we will see you in the classroom. Cue the mic.